this video, we're going to look at how to do weak acid and strong base titration problems. So if you notice here, this is a titration curve. I have pH versus the volume of base added. So I am starting with an initial acid, that's why I have a low pH, and I'm slowly adding base. You'll notice that the titration curve looks a little bit similar to the strong acid, strong base, except that the pH at the equivalence point is no longer 7. So for strong acid, strong base, we had a neutral salt. But for weak acid and strong base, it's not going to be a neutral salt. The conjugate of a strong base is negligible and can't act as an acid, but the conjugate of a weak acid is going to be a weak base. So you have created a basic salt, and that is why your pH is going to be slightly or more greater than 7 at the equivalence point when you're doing a weak acid and strong base. And it'd be the opposite if it was the opposite situation. If it was a strong acid and a weak base, you'd have an acidic salt and your pH would be less than 7 at the equivalence point. You'll also notice that this part of the line here, which we're now going to call the buffering zone, this is a little bit longer, and we'll talk about why in a moment, especially when we see calculations. So let's just talk about some calculations that you'll be doing. Initially, you'll still only have your acid present in your container if you're starting with your acid and titrating in your base. But instead here, since it's a weak acid, you're going to have a weak acid problem where you have an initial concentration and you have to do an equilibrium problem. So either an ice box with that initial concentration or plugging into that shortcut equation where H plus equals the square root of Ka times the initial acid. But either way, your weak acid isn't going to 100% ionize. So if you have 0.1 molar of your weak acid, you're not going to have 0.1 molar of H plus. You're going to have less than that because less than 100% ionizes. Okay, then along here, you're starting to add your strong base, and that strong base is going to start reacting with some of that weak acid in a neutralization, which is going to produce some of the salt, which contains the conjugate base of the weak acid. So along here, not only am I having the weak acid present, but I'm slowly adding more and more and more of that conjugate base. So essentially, I have both acid and weak acid and conjugate base present. This is what's called the buffering zone. It's really just kind of like a buffering problem, where I have some initial acid and I have some acid and some conjugate base. And since it's in the buffering zone, you can either use the Henderson-Hasselbalch equation to calculate pH. I have both the conjugate base and the conjugate acid present. I just have to put in their concentrations. Or you can just do a weak acid equilibrium problem, but your I box in that ice box will be filled with both an acid and a conjugate base initial concentrations. And those initial concentrations won't necessarily be the same as this initial concentration because some of the weak acid would be used up and some of the conjugate base would be made. I'd have to figure out what my concentrations are based on the stoichiometry of the neutralization reaction, which we'll look at. Okay, there's a special point that's halfway to the equivalence point. So if your equivalence point was at 100 milliliters, halfway to that would be at 50 milliliters. And at this special point, your concentration of conjugate base and weak acid would be equal. So the log of 1 would be 0, and your pH equals your pKa. So if they ask you a problem, they give you a titration curve, and you have to figure out what the Ka is of the acid. You go to the halfway to equivalence point, you can get the pKa, and thus the Ka. Your equivalence point is going to be controlled by your salt. In this case, it's a basic salt. It's the conjugate of the weak acid that's going to be controlling the pH, and that's why it's greater than 7. And beyond the equivalence point, you have excess base in your container. Your pH is going to be controlled by that excess base, and so it's going to just be similar to the other problems we've looked at, how much base it remains, and then using that to calculate the OH minus and then the pH. Okay, let's just practice working first with this titration curve a little bit, and then we'll get into some calculations. So on the next slide, I want you to determine the equivalence point and the pH at the equivalence point. Determine what kind of titration this is. Is it strong, strong? Is it strong, weak? What's strong, what's weak? Graphically determine the halfway point of the titration and the pH at this point, and determine the Ka. So here's your graph. Take a moment and do those things, and then check your work. To find the equivalence point, if you're having trouble, though it's kind of highlighted here, you can always kind of extend the portions of the graph above and below the equivalence point like this, and then draw a line connecting them, and then the midpoint between these these two lines would be your equivalence point. So if you're ever having trouble doing this on a piece of paper, you can feel free to do that. And if I go across, I could find that the pH roughly about maybe 8.7 or so. This is 4, 6, 8, so this is a little bit less than 9, whatever you can kind of glean from here. This must be a weak acid, strong base. Why? Because the pH of the salt is basic, so it's the anion of the weak acid that's functioning as a base. And I notice that I'm starting with the acid and I'm adding the base over time. I also see NaOH down here, which is a strong base. And at the halfway to equivalence point, I can find that I know the volume is going to be half of what's at the equivalence point. So at the equivalence point, I have 100 milliliters. I can drop down and find that. So my halfway to equivalence point would be at 50 milliliters. And if I go across, I can find the pH. I think it's a little less than 5, so I said let's make it 4.9. Your answer might be slightly different. And if I wanted to get the Ka of the acid, I can use this half equivalence point because I know at the half equivalence point, pH equals pKa. So the pKa is 4.9. I can find the Ka by taking the 10 to each side. So the Ka would be 1.3 times 10 to the negative 5. Okay, let's take a look at how to do calculations at different points along the titration. So there's really 5 different kinds of points they could ask you about, and they would never ask you really about this all in one problem on like an AP exam, but we should know how to do each point in case they ask us one of these points. So you could be asked about the initial pH. Here, you could be asked about the pH somewhere in this buffer zone, which is not at the half equivalence point, so somewhere either before or after the half equivalence point. You could be asked for the pH at the halfway to equivalence point, which is 3. You could be asked for the pH at the equivalence point, or you could be asked for the pH after the equivalence point. So those are 5 different points that we're going to talk about. And you could say, hey, if you have a titration curve, I can easily answer that. Just go across. Yeah, but what if I didn't give you this titration curve? How would you do this? Okay, so let's take a look at this. You have this weak acid reacting with a strong base. So for the neutralization that's reacting, I'm just showing you the net ionic equation here. The weak acid would not fully ionize. The OH minus and the Na plus would break up. This is a strong base. Na would be found on both sides. It would be a spectator ion. So I'm left with really the weak acid reacting fully with the OH minus to produce water and the conjugate ion of the conjugate base of this acid. And you can get this by writing a molecular equation and then getting the net ionic, but I'm just showing this as a net ionic. If you don't like working with the net ionic, you can work with the molecular as well. That's totally fine too. So let's talk about initial pH. So initially, only in my container I have my weak acid. Okay, so it's going to be based on the equilibrium of the weak acid. Here it is breaking up into H plus and its conjugate base. So I can do this with an ice box. I have the initial. I could assume that the products are 0. I could put in my change. I can I could use my 5% rule and say, hey, I'm going to assume that this is going to really ionize to such a small degree that the amount of H plus, when I subtract it from 0.1, it's still going to be close to 0.1. And put these as X and X, and I can plug into my Ka, okay, and that 5% rule, we said usually we want a difference of about 1,000 or more for the Ka and the initial acid, and we do. And if I solve for X, I get 0.00134, which makes sense. 0.1 minus 0.00134 is pretty much 0.1, so that assumption is fine. And I can do the negative log of that, and I can get my pH. Don't forget, you can also use, rather than doing an icebox, you can use that shortcut equation. This is a monoprotic weak acid, so I can plug in here with my Ka and my initial acid, take the square root, which is really what you're doing here, and I get the same answer. Okay, so that is initial acid, and those are problems we've looked at before. Let's look at point 2. If pH after 10 milliliters of the base is added. So we're going to be somewhere in what's called the buffering zone. Essentially, we're going to end up having both some of this weak acid and its conjugate ion present. So it's really a common ion problem or a buffer problem. But at this point, we really have to figure out what moles remain from the neutralization. So again, I've added some base at this point. Some of that base is going to react with that acid. I need to figure out, well, how much acid do I have left? How much remains? And how much of my conjugate ion was created at this point? Because those are what's going to be reacting here. So this is a limiting reactant problem. So I have to go to my neutralization and figure out, again, how much of that initial acid is being used up and how much remains and how much of that conjugate base is being created. So I'm going to put that ICR box again, which is really just an ice box, but rather than an equilibrium, I'm going to write what remains to kind of show the stoichiometry of what's going on. And you don't have to organize your work like this, but I find it helpful, and I put a little mini box for H2O because I'm just going to ignore it, because it's a liquid. So initially, okay, I had 0.1 molar and I had 50 milliliters of my acid. So let's mole that out. I want to be figuring out moles because things are coming from different containers. And so that's why when you're looking at your neutralization reaction, work within moles. Okay, let's figure out how much OH minus I have, or NaOH essentially. I had 0.1 molar, and at this point 10 milliliters were added, so I've added in 0.001 moles of my base. So what's limiting? My base is limiting. My base is getting completely used up, which makes sense. It's the excess acid that I have present. We said that's why the pH is lower. I still have excess acid here. And I have not yet reached my equivalence point. So if I put in, and I could assume I have 0 moles of my conjugate base to start with, because this is really hardly ionizing at all. And if I put in my minus x plus x, if I put my limiting reactant as 0, how much is getting used up? 0.001 minus x equals 0. Oh, x is 0.001. That makes sense. The OH minus is going to get completely used up, 0.001. And if I subtract the 0.001 from my initial acid, because this is a 1-to-1 ratio, right, I would get 0.004 left over. Okay, so this is what remains of my weak acid. And how much conjugate base was now made with the neutralization reaction? 0.001 moles. Notice, hey, I have both the weak acid and its conjugate base present. This is a common ion problem. This is a buffer problem. I have a weak acid and its conjugate base. This can act as a buffer. I can absolutely go into my Henderson-Hasselbalch equation now and calculate pH. Just make sure, remember, these are moles, and sometimes you might want to make sure you convert to molarities. If they're in the same beaker, they're going to have the same volume, which can be easy to plug into my Henderson-Hasselbalch, because in this case, they're both over 0.06 or 60 milliliters. Okay, well, that's going to cancel out. But if you end up actually going to an ice box instead, it's going to be important to be in molarities. Okay, so if I plug into the Henderson-Hasselbalch equation, here's my conjugate base, here's my weak acid, I get that the pH is 4.14. So anytime you're in that buffering zone, you can feel free to use this calculation, this Henderson-Hasselbalch equation. It makes life really simple. The only catch is you have to first figure out, based on your neutralization, how much acid remains and how much conjugate base was made based on the stoichiometry. So you have to remember to do that, because you're not going to have that same initial acid present. Some has been used up, and you are going to have created some conjugate base. Okay, if you wanted to instead of plugging into the Henderson-Hasselbalch equation, you can absolutely go to the equilibrium of your weak acid ionizing and plug in your initial amounts. Notice I changed them into molarities. It was before it was we were in moles, 0.001 and 0.004, but now I've changed them into molarities. Okay, and I can use my 5% rule, and notice this is just a weak acid problem, but I have conjugate base present, and when I plug in, I get that I have 7.19 times 10 to the negative 5 H plus, and I take the negative log of that. Hey, here's my pH, which is about the same, 4.14, as I did with the Henderson-Hasselbalch equation. But I think the Henderson-Hasselbalch equation is just easier to use. Sense that you still have an acidic pH because you have excess acid at this point along your titration, because you've added some base and all of that base has got neutralized and you still have some acid present, though not as much as you did initially. It is a little bit of a higher pH than your initial pH. And so what you're noticing is, once you're past the initial pH, you're really going to have to figure out what's going on with the neutralization, what remains after the neutralization, so that you have your how much acid and how much conjugate base, in this case, you have in your container to do the problem. And you're going to see this trend in all of these different pH calculations past the initial point. of really needing to look at the neutralization and figure out what remains first, and then considering either the Henderson-Hasselbalch equation or the equilibrium of the acidic or basic species that's present in your container. However, if you look at point 3, pH at the halfway point, you can feel free to go to the neutralization reaction, figure out how much acid's been used up, how much conjugate base has been created, and go to your Henderson-Hasselbalch equation. But this is a special point if you're halfway to the equivalence point, and you know this for a fact, like if let's say I'm given this titration curve and I see, oh, I'm definitely at 25 milliliters, I'm at halfway to the equivalence point, then you can know that, hey, the conjugate, the weak acid and conjugate base are in equal molarities. I have equal concentrations of them. So if I plug into the Henderson-Hasselbalch equation, that log of conjugate base over weak acid is going to cancel out because the log of 1 is 0, and I'm just going to get the pH is equal to pKa. And I have the Ka for the acid, so if I plug that in, I get that the pH is 4.74. So it saves me a lot of time of not having to go to the neutralization reaction and figuring out what remains after the neutralization in my container. I can just quickly plug in to this equation at the halfway to equivalence point. Okay, so at the halfway point, pH equals pKa. Let's look at pH at the equivalence point. In this case, when 50 milliliters of base has been added, I've reached the equivalence point, and let's actually calculate this pH with what's given in this problem. So in strong acid, strong base problems, this was easy. We would just say, okay, what's left in your container is just a salt, which is neutral, so and water, and so your pH is 7. But however, we are not dealing with a salt that is neutral. We are dealing with a salt that has acidic and basic qualities. So just like I was saying before, go to your neutralization reaction first, and let's just figure out what's in my container, how much is in my container. So at this point, I still have 0.005 moles of my acid. Initially, I had 50 milliliters of my base at this point is added, so 50 milliliters times the 0.1, I get 0.005 moles. Okay, and I can assume I have, at the start of my titration, I have none of this conjugate base present. Okay, and notice these are equal. It's at the neutralization, at the equivalence point, both of them have been completely used up. So whichever one I'm looking at, I have created 0.005 moles of my conjugate base. And this is the weakly basic species that's present in my container. So now to get the pH, I need to be looking at how this ionizes in solution, how it acts like a base. Don't forget, if I'm figuring out the stoichiometry, that I now have the moles of this. When I want to look at my ice box, let's say, with the ionization, I want to make sure I'm in molarities. So from here, once you figure out the concentration of your conjugate base, it's just a weak base problem, which I can do with making an icebox, or I can do with that shortcut equation for a base. But it's helpful to write the ionization of that conjugate base. Remember, this is the part of the salt that is basic because it's the conjugate of the weak acid. And to show it acting like a base, I'm just going to make it react with water, because that's how we show things reacting as bases, so that I get that OH minus released, and then this is going to turn into its conjugate acid, which is back into the acetic acid. Do your icebox with molarities. So remember, if you solve for the moles of acetate ion, make sure you change that to molarity by dividing by the volume. The 0.05 moles that I just solved for before divided by the 0.1 liters of total solution. And I have 0, 0 of my products to start with. Remember, I don't really have any of this left in the container because it was completely neutralized by the base. And I do minus x plus x plus x. I might not know anything at equilibrium, but I can fill it in terms of x. I can assume that x is really, really small and use that 5% rule and just carry that 0.05 down. And then the only thing that I have to keep in mind here is that in the initial problem they gave me the Ka of the acid. Well, this is not the weak acid equilibrium. This is the conjugate base acting as a weak base equilibrium. So I want to make sure that I convert the Ka into Kb by using the fact that Ka times Kb equals Kw, and Kw is 1 times 10 to the negative 14 at 25 degrees Celsius, which is in your formula sheet, and I get 5.6 times 10 to the negative 10. So it's this Kb that I'm going to be using to plug into the Kb expression. Okay, I have x, I have my weak base, in this case the weak conjugate base, the concentration of 0.05, and I have my Kb. And you might say, hey, this fits that shortcut equation where the OH minus concentration equals the square root of Kb times the initial base, and it does. So really all you're doing is you're finding your conjugate base that you have in your container based off of the neutralization reaction, because the acid and base have neutralized and they've created the salt, and this is part of the salt that was created. And then I'm just using this in a weak base problem. You just have to change the Ka into Kb, because now you're working with the base rather than the acid. And I get that x is 5.3 times 10 to the negative 6, so that was a valid approximation. 0.05 minus 0.0000053 is essentially 0.05. Take the negative log of that to get the pOH, subtract from 14 to get the pH, and I get 8.72. And it makes sense that this is the pH for it to be, this is a weakly basic ion, so I should get a basic pH. And that's why the pH is not 7 at the equivalence point. So again, you're always going to the neutralization reaction, figure out what remains in your container. Okay, in this case, it's going to be the conjugate base, and then use that here now to solve a weak base problem. Okay, pH after the equivalence point, it's going to be controlled by the excess base, but again, we still have to figure out what's going on in our container after, what's left in our container after the neutralization. So we're always going to be kind of starting with a limiting reactant problem. Going back to my net ionic equation for the neutralization, and if you don't like the net ionic equation, feel free to use a molecular equation instead. It's totally fine. I like the net ionic because then I actually see the conjugate base by itself, but as an ion, but you'll just see it as a salt instead. So I have, here's my initial acid that I had, here's the amount of base that I've added so far, 0.0075, ignore water, and I don't have any of the conjugate base to start with, and I'll notice that, hey, I'm going to have excess base. All the acid has been neutralized at this point. All this weak acid is completely used up, so I have 0 at the end, and I can see that, hey, 0.005 must have been used up, so I'm subtracting 0.005 from my base, and I get that I have 0.0025 moles of base left over. Again, you can do this just in terms of stoichiometry. I like to arrange it to look like this. So I have my moles of OH minus left over. Don't forget, if we're doing pH, we've got to be changing this into molarities. Okay, and I also have 0.005 moles of my conjugate base that was made, but OH minus is such a stronger base than this conjugate base. We saw that it had a really small Kb, that the amount of OH minus that's coming from this is going to be negligible. So it's really just going to be controlled by my excess base, strong base that I have in my container, which is 0.0025. Okay, so remember, this is a strong base. It 100% completely ionizes, so my OH minus concentration is going to be given by the concentration of my base that's left over as well. The 0.0025 moles divided by my volume that I have total in my container at this point, and I get 0.02 moles of my OH minus. Take the negative log of that, I can get the pOH, and then subtract from 14 and I get 12.3. So this is not an equilibrium problem because I have excess strong base, and the strong base completely ionizes. I have my OH minus concentration right here without doing an icebox. Okay, so this is in your notes as well, just initial pH, that's the weak acid equilibrium. Your pH between initial and equivalence point, that's when you're using your Henderson-Hasselbalch equation, but you first have to go to the limiting reactant problem. You first have to use a neutralization to figure out what's left in your container. How many moles of acid are left over, and then the molarity of acid, how many moles of conjugate base, and the molarity of base. At the pH that's halfway to equivalence, these two values are equal, so my pH just equals pKa. pH at the equivalence point is going to be controlled by your basic salt. You go to the neutralization reaction, figure out how much conjugate base was made, And then from there is just a weak base problem, but don't forget to convert the Ka to Kb. All right, and then beyond the equivalence point, it's controlled by the excess base. So again, limiting reactant problem, figure out what remains in your container, and then you'll have your moles of your base turn to molarity, which is your molarity of your OH minus if it fully ionizes, get your POH and your pH.